Hello, we're going to look at an equilibrium problem here. Our condition is we have a ring with 3 different ropes pulling on it, but it's maintained in equilibrium, so it's staying at rest. And we have ropes pulling in 2 dimensions, so we're looking down on a table from like a bird's eye view here. Rope 1 pulls with 111 newtons directly northward. Rope 2 pulls with 225 newtons at 25 degrees north of east. So just real quickly there, north of east is measured up from here at 25 degrees. So, as always with a force problem, we're going to start by drawing a free body diagram. And so here we have the north-south direction is my y-axis and the east-west direction is my x-axis. I have T1 directly in the positive y direction, and T2 and T3 at angles, and there's no acceleration because this is at rest and in equilibrium. So it's in equilibrium in both the x and y directions. So I'm just going to start first by writing my Newton's second law equation for the y direction, and it's at equilibrium, so there's no acceleration, and the net forces all cancel out in the y direction. And when we go ahead and write our force equation, we have no acceleration, so the net force is equal to 0, and I'm going to add up the forces in that direction. And the first force I have, I'm just going to go down to my free body diagram down here and check that out. So my first force I have here is T1, and it's directly in the positive y direction, so all of it upwards. And the next force I come to is T2, but it's pulling also upwards, so it has a positive number right here, but only some of it is in that direction, so I put a little subscript y to help me remember just part of it is in that direction. And I also have T3 downward, so I have a negative sign, and it's not totally in the y direction, so I have a little subscript y for indicating just some of it. And when I put in the known information here, I know T1 is 111, T2 is 225, but for the sum of it component, I want to go ahead and put in a little, multiply it by a trig function to handicap it, so there's only not 100% of this force is in that direction, just part of it. And so let's go ahead and draw this T2 vector and see what its little component triangle is going to look like here. So I have T2 up and to the right. It has a horizontal component to the right and a vertical component upward. So that's your horizontal component of T2x and vertical component of T2y. 25-degree angles right here north of east. So I'm going to multiply by sine 25 right here to indicate that it's not all of this, it's only part of it. And then T3y, we're solving just for the vertical component of this vector right here. And when we do that, we get out of here, do a little bit of math, we get approximately 206 newtons. So the next thing I'm going to do is write a force equation for the x direction. And it's in equilibrium also, so I'm going to set it equal to 0. And as we start walking through this free body diagram here, I'm going to start with T2, and it pulls to the right, so I'm going to have a positive value here. And the next thing, and it's only part of it is in that direction. It's not totally rightwards here. It's up and to the right, so only some of it is in that direction. I indicate this with the little subscript x right here. And I have T3, and only some of it is going to be in the x direction. It's not pointed directly rightwards, it's down and to the right. So only part of it's in that direction. I indicate that with the little subscript x. And I start putting in my known information. I have 225 is the tension T2, but I only want my x component here. So I'm going to have to multiply by some trig function. And if we're really thoughtful about T2y, and we said it was sine 25, well, we know that this has to end up being cosine of 25. And so we're trying to, once again, grab the adjacent side to this angle. And then T3y, just some of it is acting in the horizontal direction here. And when we solve out, we get 204 newtons for the component of T3, for the vertical component of T3.